All right, guys, so this is our third rice chart video, but really the main thing I want you to get from here is when you would do a Q calculation and why you do a Q calculation and what does Q tell you compared to K, all right? So basically, what it comes down to is K is the equilibrium position of the reaction. So K is basically the ratio of products over reactants when you're at equilibrium. What Q would represent is the same exact expression that K is. And so a simplified version would be Q is equal to products over reactants, but it would just be the amounts of products over reactants at any point. So maybe the initial amounts of products and reactants, or maybe you don't know, just somewhere along the timeline of the reaction as it's approaching equilibrium, but you're just not at equilibrium yet. So Q is where the reaction is right now compared to in terms of the amounts of everything, and K is where it's going to get to, all right, to establish an equilibrium as long as the temperature stays the same. So if you're not sure you're at equilibrium, or you're not sure which way the reaction needs to shift to reach equilibrium, meaning to reach an equilibrium, to establish an equilibrium at this temperature, do I need more products compared to the amount of reactants that I have right now? Or do I need more reactants compared to the amount of products I have right now? A Q value, comparing it to the K value, the equilibrium position, will tell you which way the reaction is going to shift in order to get to the equilibrium position, which is the K position. So Q is where you're at, K is where the reaction needs to get to be at equilibrium, all right? And so that kind of goes hand in hand with the rice chart when you're unsure of what the change is going to be in your rice chart. So if you remember, your rice chart is reaction, initial conditions, change in those conditions, and change in those amounts, initial molarities or partial pressures, change in those molarities or partial pressures, and then the equilibrium amounts, molarities and partial pressures. And so that change, the rice charts we've been doing, we've always done minus on the reactant side and plus on the product side, only because we've always started out these problems where we don't have any product. And if we don't have any product, we know the reaction has to shift towards the products in order to reach equilibrium, because you have to have some of everything to be at equilibrium. But now I'm going to give you a scenario, or eventually I'll show you in this video, I'll give you a scenario where you start with some of everything. Like, here's a reaction, it has these reactants, it has these products, and I throw some of everything into the container, and I want to know when equilibrium is established, how much of everything am I going to get? And so the question is, well, in order to reach equilibrium, do I need to lose some product and gain more reactant, or do I need to lose some of the reactant and gain more product? And that's where Q will come in. All right, so let's get into the lesson. All right. So again, Q is equal to the same expression that K is, but Q is for non-equilibrium amounts. K is for equilibrium amounts. Okay? So if I have my equilibrium molarities and I plug it into the equilibrium expression, the value that comes out will be K. But if I plug in molarities that aren't the equilibrium into the equilibrium expression, the value that comes out will be a Q value, because a Q value means you haven't reached your equilibrium. Okay? Now, if Q equals K, then yes, you're at equilibrium. All right? All right. So here's a scenario, okay? Or not a scenario yet, but just let me show you what I mean. Right? If this is my reaction, and I said do a Q calculation, well, Q would equal the same expression that K is equal to. So products over reactants, coefficients become exponents. So Q is equal to that expression, K is equal to that expression. The problem is, or not the problem, but the difference is, if you're plugging in equilibrium molarities here, then you get a K value. If you're plugging in initial molarity values here, then you get a Q value. And you're not at equilibrium yet. Okay? So you need, so if you have non-equilibrium values, you plug it into the expression and you get a Q. If you do have your equilibrium values, you plug it into the expression and you get K. All right. So again, the thing about comparing Q to K, Q is where the reaction is right now, and K is where it's going. K is where it's got to get to. K is when it's going to reestablish its equilibrium. Okay? Q is any moment during the reaction as it approaches equilibrium. K is when it's at equilibrium. K is the equilibrium position. So Q is your current position, K is your equilibrium position. And you're always going to be moving towards the equilibrium position. So Q is where you're at, K is where you need to get to. Okay? All right, so let's look at this question. So first, I just want to review some race chart stuff and show a equilibrium problem where you don't need a Q calculation. So here, we're given a reaction, and we're told we mix 3 moles of this reactant with 1.5 moles of this reactant in a 2-liter container, and it's found that at equilibrium, we only have 1 mole of oxygen. So the amount of oxygen went from 1.5 to 1 mole, and based on this, we want to find the equilibrium concentrations of everything, and we want to find the equilibrium constant, K. All right. So just to understand, and I'll maybe say this again, if you don't have a K value, if you're not given K, or you haven't found K yet, there's no reason to think that you have to do a Q calculation. The only reason you would be calculating Q is so you can compare it to a K value that you know. So you've either been given it or you've solved for it already. So in this scenario, right now we're not worried about a Q calculation because we don't have a K value to compare it to. That's what we're going to figure out in part B. All right. But here, this is where I want to kind of show you where you got to be careful. We can set up our rice chart, but remember what goes in a rice chart: molarities or partial pressures. Right now, we were given moles. And if we had put this many moles in a 1-liter container instead of a 2-liter container, then 3 would be the molarity of SO2. But the initial molarity of SO2 isn't 3, it's 3 divided by 2, right? The initial molarity of oxygen isn't 1.5, the initial molarity of oxygen is 1.5 divided by 2. The equilibrium molarity of oxygen isn't 1, it's 1 divided by 2. So for part A, right away, I can answer for one of these. I can get the equilibrium concentration for oxygen. It's just 0.5, 1 divided by 2, because that's how many moles I have of oxygen at equilibrium. That's the volume of the container. And so 1 divided by 2, 0.5 moles per liter would be the equilibrium concentration of oxygen. But I still need to figure out the equilibrium concentrations of these two things. All right, so let's set up our rice chart. So again, notice I didn't put 3 here, I put 1.5 because I had to do 3 divided by 2, right? And here I put 0.75, not 1, because I had to do 1.5 divided by 2. All right, so you only, when you're making your rice chart, make sure you're not plugging in moles. Make sure you're plugging in molarity or partial pressures, okay? So initially, I don't have any of my product. So that's all I started with. So so in this case, since I know I have 0 product, I know the reaction's shifting to the right to reach equilibrium. So that means I'm going to lose this stuff and I'm going to gain this stuff. So I know in my change, it's going to be minus on this side and it's going to be plus on that side. All right. But remember, stoichiometry matters. So it's not minus X for the SO2, it's minus 2X. It's minus X for the oxygen because my coefficient's 1, and it would be plus 2X for the SO3, okay? So at equilibrium, the SO2 is going to be 1.5 minus 2X, so 1.5 minus 2X. The oxygen is 0.5 because we were told, right? But if we weren't, it would be 0.75 minus X, but we were told that it's 0.5, right? We were told that it's 1 mole in 2 liters at equilibrium. So we know that its equilibrium concentration is 0.5. And then this would be 0 plus 2X. So the concentration of SO3 is going to be 2x at equilibrium. Okay. Now, because we have an initial and a final amount, and we know what the change is, we can calculate x. So we can say 0.75 minus x equals 0.5. So we can solve for x. We get x, 0.25. And then now that we have what x is equal to, I can multiply it by 2 to get the concentration of the SO3. I can do 1.5 minus 2 times this number to get the concentration of the SO2. All right, so we do the math and we get our equilibrium concentration of SO2, our equilibrium concentration of oxygen, and we get our equilibrium concentration of SO3. So we knew the oxygen already, and we used our Rice chart to figure out the equilibrium concentration of SO2 and the equilibrium concentration of SO3. Okay, so the other part of this question was calculate the equilibrium constant, so let's go ahead and do that. So now all we have to do is plug these molarities into the expression. So K would equal the concentration of SO3 at equilibrium squared over the concentration of SO2 squared times the concentration of oxygen. So we plug in our numbers and we get, at whatever temperature this is happening, our equilibrium constant for that reaction is 0.5. Okay. So now let's show the same kind of similar setup, but where a Q calculation would come in. All right. So now notice we're given the equation, and I'm guessing, and so the reaction must be happening at the same temperature from the previous problem, because notice the K value is the same. And remember, the only time K changes is when temperature changes. All right. So we're given the reaction this time, and we have a K value. So that's kind of a clue. Every time we're given a K value, doesn't mean you always have to do a Q calculation, but if you know what K is, keep it in the back of your mind. Maybe a Q calculation can help you. All right. So the question is, we want to know what the equilibrium concentrations will be when we put 1 mole of each gas in a 3-liter container. So each of these gases, all of the gases, including the product. So we're putting 1 mole of this in the container, 1 mole of that in the container, 1 mole of that into the container, and we're letting them react. And then we want to come back at equilibrium and know how much of each gas we have at equilibrium in terms of their molarities. All right. So again, if I'm starting my Rice chart, I'm not going to put in 1 for the initial amount of everything. I got to do 1 divided by 3, so 1/3. So we got 0.33 molar of this, 0.33 molar of this, and 0.33 molar of this. Okay. So this is a different type of Rice chart for us, because our previous Rice charts that we've done with practice, we've always had 0 product. Now we have non-zero product. We have some of everything. Now, if one of these were a 0, one of our reactants, the reaction would have to shift to the left to reach equilibrium. And so it would be minus on this side and plus on this side for the change. But right now the question is, which way does the reaction shift to reach equilibrium? If at this point in the reaction, if we have too much reactant and not enough product, the reaction is going to shift this way. And so I'll put minus on this side of my change and plus on this side. But at this point in the reaction, if I have too much product and not enough reactant to be at equilibrium, the reaction is going to shift to the left, and I'm going to lose this and gain this. So in my Rice chart, it would be minus over here and plus over here. So one reason to do a Q calculation is if you're making your Rice chart, but you're not sure where to put the minus signs in the change part of your Rice chart and where to put the plus signs. Okay? Right? If we go back to the original problem, the original Rice chart, I know that it's minus on this side because this is 0. And so the reaction has to shift to the right to reach equilibrium. All right, so now let's go back to this scenario. So when you're trying to figure out which way the reaction is going to shift to reach equilibrium based on the position you're at right now, that's when you do a Q calculation. You do a Q calculation and you compare it to K. So what's Q equal to? Well, Q is equal to the same expression that K is equal to. It's just the initial concentrations, not the final. So we plug it in, we plug Q, the initial concentrations into the equilibrium expression, and that'll give us a Q value. So they were all 0.33, so we plug those in, and we get Q equals 3. And so now we have Q, and remember we were originally given K, So we compare Q to K. And really all you care about is Q greater than K, is Q less than K, or is Q equal to K? If Q was equal to K, then we would be at equilibrium. Like if Q came out to be, if we did this and Q came out to be 0.5, then these would be our equilibrium concentrations. Okay? But if Q is not equal to K, then I know for sure that those aren't my equilibrium concentrations, and we got to figure out what they are. So what does Q being greater than K mean? It means you have too much product. So we, at this point, our current position of the reaction, we have too much product and not enough reactant. So in order to reach equilibrium, we need more reactant and less product. So what does that mean? It means the reaction is going to shift to the left. So we're going to lose product and gain reactant. So now we're going to have a Rice chart where we're doing plus X on the reactant side and minus X on the product side. We still have to include the coefficients, okay? But the reason why I know it's plus on this side and minus on this side is because Q was greater than K. So now, at equilibrium, this is going to be 0.33 plus 2x. This is going to be 0.33 plus x. This is going to be 0.33 minus 2x. So now, how are we going to actually solve for x? Well, we know what K is, and now we have our equilibrium concentrations in terms of x. We can plug those in to our equilibrium expression. Now remember, this is the equilibrium concentration of the SO3, but remember in the expression you got to square it. So it would be that concentration squared over that concentration also squared because of that coefficient, and then times the oxygen concentration, but not squared because that coefficient was 1. All right, so now we're in a position where there is no simplification here. We'd have to solve for x. So understand that this exact question would not be on the AP exam. The way they would ask this question on the AP exam is they would just say, you know, something along the lines, when equilibrium is established, would the concentration of oxygen be greater than it is initially or lower than it is initially? And so you would do your Q calculation and you would say, oh, well, Q is greater than K, so the reaction has to shift to the left. So I know that the oxygen concentration at equilibrium is going to be greater than what it was initially. And that's what you would have to answer. You would not have to graph to solve for x here unless there was a way to simplify, but there's no way to simplify this, all right? So I'm going to go ahead and answer the question for you. If you graph to solve for x, and the way you would do it here is you would say, okay, I would make y1 equals 0.5, and then I would make y2 in my graphing calculator equal to this expression. Now, a lot of things can go wrong here. You got to make sure you're using parentheses in all the right spots. If you don't use parentheses where you need to, you're not going to get the right graph and that kind of thing. All right. But when I graph to solve for x, and remember, a lot of times you can get multiple intercepts, you can get multiple x values. The only one x value would make sense for the reaction, and you might have to test all of them. All right. But the x value that works in this scenario is 0.064. So I graphed to solve for x, I got 0.064. And so again, if I plug in 0.064 into these expressions for my Rice chart, I get all my equilibrium concentrations. So now I have all my equilibrium concentrations. And notice the equilibrium concentration for my product was less than the initial, 0.33, but my equilibrium concentrations for my reactants are greater than the initial 0.33, and that's because Q was greater than K. The reaction had to shift to the left to get to the equilibrium position, all right? And you can check yourself, right? Plug these values into the equilibrium expression and see if you get 0.5, because that's what K has to equal. And so if they don't come close to 0.5, then you know maybe I used the wrong X value for when I graph to solve for X, or maybe I didn't enter this in my calculator correctly. But again, you're not going to actually have to do that on the exam, because you would, if you had to go this far in this question, there would be a way to simplify. But there's not a way to simplify for this one, right? If we plug them in, when I plug those numbers in, I get 0.49, so pretty much zero point 0.5. So that was the correct x value when I graphed to solve for x and that kind of thing. Okay, so these are our equilibrium concentrations. Okay, again, the Q calculation, you will have to do some Q calculations, but you wouldn't have to take it this far to actually solve for x here. You just have to know, okay, well, if the reaction has to shift to the left to reach equilibrium, what does that mean about these concentrations compared to those concentrations? Are they greater than, less than, right? That kind of thing, equal to, whatever. All right. So that's our kind of last, maybe last, I don't know. If I have some more inspiration to make another rice chart video, I will. But those are kind of a lot of different rice chart scenarios. We'll be using rice charts a lot. And then we'll, later on this unit and in unit 5, we'll be making our shortcuts. But anytime I refer to an equilibrium shortcut, whether it's a KSP shortcut, which we'll get to in 4-4, a weak acid shortcut or a weak base shortcut when we get to 5-1, all of those shortcuts are created by rice charts, and then we make a simplification. So the shortcut is just memorizing the shortcut so you don't have to waste time making the rice chart. But if you forgot the shortcut, then you can always just make a rice chart and figure out what it was. All right, so anyway, but again, we'll cover that a lot in class, hopefully. And hopefully it'll make sense as we move forward and you do more practice and we see more examples. All right? All right, have a good one. Whoops, I'm still recording. Click the wrong button.